In this lesson, we're looking at projectile motion. Now, projectile motion is very similar to what we've already looked at in our lessons on velocity, acceleration, and position for motion, and motion in a straight line. Now, the entire idea with projectile motion is that we're looking at a scenario where an object is being projected into a two-dimensional plane. Now, because we're technically working in a three-dimensional plane, the idea is that the two dimensions we're considering are a vertical dimension and a horizontal. Now, where the horizontal may have a direction, we're not going to consider it. Now, the idea with projectile motion is this object that is projected will be projected at some angle with a given velocity, and the angle that's projected at will generally be from the horizontal. Now, that means that there's only a couple of little thoughts we need to consider to be able to look at scenarios with projectile motion. So the first one is that the initial velocity and angle of projection can be used to determine the velocity in each of the components. So the horizontal in the I direction and the vertical velocity in the J direction. So essentially this is what we're looking at. We're looking at some velocity at a given angle from the horizontal. Now, because this is a trigonometric scenario, we can use v sine theta to get our vertical velocity. So this is this vector component. And to get the horizontal, we can use v cos theta. Okay, now the second thing is that we can always begin with a known acceleration vector. Now, this is because generally when we look at projectile motion, we assume air resistance is negligible and gravitational acceleration is constant. So if we make these two assumptions, it means that we can say that the acceleration at any point in time is always going to be zero in the I direction because there's no air resistance acting against, and negative g in the J direction. Now, if we're on Earth, obviously gravity is going to be 9.81 meters per second squared. Okay, so those two bits of information, the fact that we can break the initial velocity into components, and we can always start with a known acceleration vector, means that we can now set up any scenario as long as we're given some basic information. So we'll look at a couple of examples here. Okay, so when we look at this example, the question is an object is projected at 30 degrees above the horizontal at 50 meters per second. If it's initially launched from a platform 10 meters high, then we can calculate its greatest height and its horizontal distance. So, with these projectile motion questions, before we do anything in terms of solving the actual question, we'll need to model acceleration, velocity, and position vectors. So from the given information, we know that when t is equal to 0, if we look at the initial velocity being 30 degrees above the horizontal at 50 meters per second, then we can say this horizontal component is going to be 50 cos 30, and the vertical component will be 50 sine 30. So when we simplify that, this becomes 25, and this becomes 25 square root of 3. So that means that we can say v initial is 25 square root of 3 in the I direction and 25 in the J direction. Now also when t is equal to 0, we've got an initial position, so our Ri will just be 0 in the I direction, and because it was launched off a platform that was 10 meters high, and 10 in the J direction. So that'll mean that we can calculate those c values nice and easily because these will always be polynomial functions. Okay, so a is equal to 0 in the I direction and negative 9.8 in the J direction. And we know the velocity will be the integral of the acceleration, so it will be the integral of 0 in the I and negative 9.8 in the j with respect to t. So this becomes 0t plus c, which of course we know that's 0 in the I direction, and negative 9.8t plus c2 in the j direction. Now, because this is what we're going to use this initial for to give us this c1 and c2 value. So now we get 0t plus c1, and c1 is just going to be 25 root 3, as it's the initial horizontal velocity. And in the vertical plane, we get 9.8t plus 25, because that 25 is the initial vertical velocity. So we've got our acceleration and our velocity vectors. Now we can find our displacement vector. So displacement will be the integral of velocity, which is 25 root 3 in the I direction and negative 9.8t plus 25 in the j direction, or with respect to t. So that gives us 25 root 3t plus c1 in the I direction, and the c1 will be the initial displacement. Add 1 to the power divided by the power, so we get negative 4.9t squared plus 25t plus c2 in the j direction. And again, we can make these links here. We can see that this is going to refer to the c1 and the c2 values, and we can say that r is equal to 25 root 3t plus 0, so we can leave that as just j, and negative 4.9t squared plus 25t plus 10 in the j direction. Okay, so now that we've got this, we can solve what we need to solve. So these three equations, and probably more correctly the velocity and position equations or vector functions, will allow us to be able to solve. Okay, so the first one asks us to find maximum height. So to find the maximum height, we need to be able to interpret well enough to say, okay, the maximum height is when the vertical velocity is equal to 0. So if we can make that statement, we can see that in that projectile motion, at this point here, we've got that vertical velocity is at a change from being positive to negative. So there's this point where the vertical velocity is equal to 0. So if we say that 0 is equal to the vertical component of the velocity, we can rearrange to isolate for time, and that will allow us to find the time of the greatest height. We can then use that time to sub in and find the actual height value. So 0 is equal to negative 9.8t plus 25, which is 9.8t is equal to 25, and t is equal to 25 on 9.8. And that will be approximately 2.55 seconds. So then if we look at the height at 2.55 seconds, so now we're looking at subbing into this height equation here, which is the vertical component of the position, we get negative 4.9 times 2.55 squared plus 25 times 2.55 plus 10, and we get our height. So our maximum height will be 41.89 meters. So there's the first part of the question answered. The other thing that we had to find is the horizontal distance traveled. So the second thought will have to be at the end of the entire projection, where we start at 0, 10, this final point is going to give us our horizontal distance, and we should be able to see that the height here is 0. Now if we can do that, that gives us the information that we need. So we're looking at when the height is equal to 0. So we're saying 0 was equal to negative 4.9 t squared plus 25t plus 10. So using our calculator, we can solve this really quickly, and we end up with a solution of t is equal to 5.4748 or negative 0.372. Of course, we can disregard that one, and we'll say that t is approximately 5.47 seconds. So our last step is we want to find that horizontal distance. So we're saying that x, that horizontal distance, will be 25 root 3 multiplied by t, because that is the equation that allows us to calculate the horizontal distance. So multiply by 5.47, and we get a horizontal distance of 236.86 meters. Okay, so that concludes that question. There's more complicated scenarios with this, so we'll look at one really quick scenario where we have to solve for other information. Okay, so in this second example, we're looking at an object that's projected at an unknown angle and speed. If it's in the air for 10 seconds, so we know that information, it's in the air for 10 seconds. It's launched from an initial height of 2 meters and travels 150 meters horizontally to determine the launch angle and the initial velocity. So we can start off the same way. We know that the initial acceleration is 0 in the I and negative 9.8 in the J, because we can make the assumption again that air resistance is negligible and that gravity is constant at negative 9.8. We know that when t is equal to 0, because the velocity is unknown and the angle is unknown, all we can do is break it into its components and say that this is v cos theta and v sine theta. So v initial is v cos theta I and v sine theta j. R initial is just going to be 0 and 2, the I and j. So now that we have that, we can go through the process of getting the vector functions for velocity and displacement or position. So v is the integral of 0 I and negative 9.8 j with respect to t, which gives us c1 in the I direction and negative 9.8 t plus c2 in the j direction. So we're left here with v cos theta I and negative 9.8 t plus v sine theta in the j. Now be really careful here. You can see this theta is a constant. Same with v, so the velocity and the launch angle are, I guess, parameters. The variable that we're dealing with is t. Our job is to calculate the velocity and the theta. Right, so the next step is we want to find our displacement vector. So we can say it's going to be the integral of the velocity vector with respect to time. And so that means we'll end up with v cos theta t plus c1 in the I direction and negative 4.9 t squared plus v sine theta t plus c2 in the j direction. So c1 is 0 and 2, so now we've got v cos theta t plus 0 in the I and negative 4.9 t squared plus v sine theta t plus 2 in the j direction. Now, the information we're given is that when it lands, it's traveled 150 meters. So that tells us that x is equal to 150, time is equal to 10, and its final height is equal to 0. So if we put this straight into this position vector, we can say that 150 is equal to v cos theta t, and 0 is equal to negative 4.9 t squared plus v sine theta t plus 2. Now if we put in the time of 10 seconds, we get 150 is equal to 10v cos theta, or 15 is equal to v cos theta as our first equation. We get 0 is equal to negative 4.9 times 10 squared, so times 100 gives us negative 490, plus 10v sine theta plus 2, and when we combine that and then add across, we get 488 is equal to 10v sine theta. Now if we divide by 10, we get 48.8 is equal to v sine theta for a second equation. So the final bit of this is quite simple. We can see if we divide, if we say 2 over 1, then we get 48.8 on 15, which is easily calculatable. And we have v sine theta on v cos theta. And the v's will cancel, and sine on cos is tan. So we end up with tan theta is equal to 48.8 on 15. And if we want to find the launch angle, then it's going to be arctan of that ratio. And we end up with an angle that's approximately 72.9 degrees. Now, to find our velocity, all we need to do is sub back into one of the equations. So let's say 15 is equal to v cos 72.9 degrees. So v will be 15 on that. So v ends up being approximately 51.05 meters per second. Okay, so we can see it's a little bit different. We've got a simultaneous process as part of that problem. And we can come up with in the end that our launch velocity is 51.05 and our launch angle is 72.9 degrees. We could then go on to do whatever we needed to do with it as the question poses. In this one, it was just find those two values. There's plenty of other little tricks in projectile motion, but I think that probably covers enough for now. That concludes the lesson on projectile motion.